Hello and welcome to our energy systems video about how small modular nuclear reactors can be used as a load-following technology. First, let's start with a few definitions to help us understand the topic. This is a load duration curve. It describes how much electricity an area uses each hour of the year. It's organized from highest load to smallest for clarity. The total capacity requirement is the amount of electricity that must be generated in a particular hour. Technologies that are large, but with a low variable operating cost, are the most suited to generating the green block. This can be a coal plant or a large nuclear power plant. This is called a baseload capacity. The middle region is a load-following capacity. Most commonly, this is satisfied with fossil fuel burning plants. The small orange area is produced by inefficient but low initial cost technologies, called peak load capacities. This could be a peaker gas plant or a diesel generator. The next important concept is cogeneration. This is when electricity is generated alongside another type of energy or service, such as heat. There are some requirements for a cogeneration technology to be viable. There must be a demand for the electricity and the other service produced. The technology consuming the energy must have adequate input and should be flexible enough to increase or decrease production on demand. One last concept is dispatchable. A dispatchable technology can change the amount of electricity produced on demand. This is an extremely valuable property because this makes meeting electricity demand much easier. Renewable resources such as solar panels and wind turbines are not dispatchable, but fossil fuel burning plants are. So much of the load following capacity is fulfilled by fossil fuel technologies. Currently, nuclear power is the largest source of dispatchable carbon neutral electricity. Since large plants are slow to ramp up and down, it's only being used as a base load. But what if it could be dispatched quickly, replacing fossil fuels? This brings us to small modular reactors. They follow the same principle as large regular nuclear reactors, except they are small. They are made in a factory, then shipped to the plant location. A set of small modular reactors can be built next to each other in order to have the same output as a large reactor, but be more flexible in terms of where they send their energy. Let's compare how a large reactor and a set of small modular reactors can be used as a load-following capacity. Say the electricity demand is high. Both reactors perform the same function. All of the electricity goes to the grid. When demand is low, the large reactor can only reduce its output. This isn't viable because its revenue is lower while maintaining virtually the same operating costs. The set of small modular reactors can output some electricity to the grid, but also support desalination, district heating, or hydrogen production, assuming the local economy can support one of those activities. There are many kinds of small modular reactors. Here are a few examples. We will only look at 3 in detail. The first one is a pressurized water reactor. There are 2 main types, light water and heavy water, also known as CANDU. This design outputs electricity by means of a turbine. It also outputs steam, which is extremely convenient for district heating. The next design is a fast neutron reactor. It's similar in output to pressurized water reactors, but a bonus of this technology is that its waste is easier to handle since it burns the longer-lasting radioactive waste. Unfortunately, this design is expensive to operate and construct. The last design is a high-temperature reactor, which is different from other designs because they use coolants that can function at much higher temperatures, around 1,000 degrees Celsius. This is well suited for hydrogen production, since the chemical reaction to produce hydrogen, the sulfur iodine cycle, needs very high temperature inputs to react. In summary, small modular reactors are a key aspect to a carbon neutral future because they are carbon neutral, dispatchable, flexible, and varied in their output. Thank you for watching.